Hello everyone, my name is Putra and today we are going to discuss about Wheatstone Bridge and the experiment that I have done. Now, the overview of Wheatstone Bridge is a bridge circuit in its simplest form that consists of a network of four resistive arms forming a closed circuit, with a DC source of current applied to two opposite junctions and a current detector connected to the other two junctions. In the experiment, we measured resistance of the wires that 1 meter length, but they are different for cross-sectional area. In addition, the resistance of wires made of different materials with the same cross-sectional area and length will be examined. Now, the typical Wheatstone bridge, we have 4 resistors. 3 of the resistors have known values, one of which is variable or adjustable. Now, the 4th resistor is not known, and we are going to search for it. Next is the Wheatstone bridge equations. R3 equals R1 divided by R2 times R4. Now, R3 is the 3rd resistor that we don't know. Now, how do we search for it? We use R1 divided by R2 times R4, which is the resistance that we have known. And then, how do we search for Rx or resistance? We are going to use Rc times L1 per L2, which is L1 is the what? How do we search for L1? We are going to search it with 1 meter converted to millimeter minus the time we are going to see the length that is going to take to that the multimeter is going to show 0. And L2 is going to be the same. Now, R equals rho times L divided by A. Rho is the type of the material that we are going to use, and R is the resistance. L per A is the length, L is the length, and A is the area. Now, we can use 2 more equations to search for resistance. Resistance R equals rho times L divided by pi times R squared. Now we can use that or this. R equals rho times 4 times L divided by pi times d squared. D is diameter and R is radius. Now how do we search for deviation? Deviation is in percent. We are going to use Rx divided by actual Rx times 100%. Tool for the experiment. Now, the tool for the experiment is resist board, 1 slide of wire measurement bridge, 1 connection box, 1 power supply, 1 multimeter, 1 cable, 1 red cable, 2,000 meter red cable, 1 yellow cable, 2 1000 millimeter yellow cable, 1 500 millimeter blue cable, 1000 millimeter blue cable, 1 resistor ohm, 1 resistor 2 ohm, 1 resistor 5 ohm, 1 resistor with 10 ohm, 1 resistor with 47 ohm, and a resistor with 100 ohm, a resistor with 150 ohm, a resistor with 220 ohm, a resistor with 330 ohm, and a resistor with 680 ohm. And the last is adhesive tape or a plug. First experiment procedure. We have to set up the circuit as shown in the picture, and then we are going to use the junction box to place the resistor with an unknown value, R or Rx, which in this setup is R1, and the combination resistor with a known value or Rc, which in this setup is R2. Connect the resistor to the output of the power supply using short red and blue wires. Use similar wires to connect both resistors to the slide wire measurement bridge. Connect the point between the 2 resistors Rx and Rc to one of the input terminals of the ammeter. Now, using a yellow wire. And then we connect the other input terminal of the ammeter to the slider of the potentiometer, and then we adjust the slider of the slide wire so that the multimeter shows 0 current. The slide position depends on the ratio of the 2 resistors. If you cannot find a slide position that is only 0, it is likely that the ratio of the 2 resistors is too large. Record the slider reading on the measuring scale and the position L2 equals 100 cm and repeat steps 1 to 6 for other values of Rx. Next is the second experiment procedure. In this purpose, arrange the circuit as the experiment A, but replace the resistor RC with a resistor of approximately 1 ohm, and replace the resistor Rx with a 2Ni 44 wire. Once the circuit is correctly assembled, apply voltage from the power supply. Since the resistance of the wire is very small, start with a relatively low voltage. Pay attention to the indicator light on the power supply. If it dims, reduce the output voltage. Now, then we adjust the side pressure until a balance condition is reached or the multimeter shows zero current. Record the side pressure on L1 and L2. This is the first experiment data sheet. Labeling Rx1. The RC we are going to use is 330, L1 is 247 mm, and L2 is 753 mm. Actual Rx is 100, and Rx that we find is 108.2. Rx2 we use 330, and then L1 we use actual Rx is 150, L1 is 329 mm, L2 is 671 mm, and Rx is 161.8. Rx3, L1 is 430 mm, L2 is 570 mm, and actual Rx is 680 ohm. Rx is 437.4. Second experimental sheet. Diameter. The first one is using 1 mm of diameter. L1 is 388, L2 is 602. The error that we find is 43.6 times 10 minus 16. A is 3.14. L per A is 259.87. 0.7 millimeters is 394 millimeters. L2 is 606 millimeters. Resistance is 92.6 times 10 times minus 16. A is 1.538. L per A is 551.36. 0.5 L1 is 261 millimeters. L2 is 739 millimeters. R is 409 times 10 times minus 16. The A is 0.785 squared millimeter squared. L per A is 2,435.66 millimeter per millimeter squared. 0.35 diameter is, we have L1 is 128 millimeters, L2 872 millimeters. Resistance is 1,302 times 10 times minus 16. Area is 0.388 millimeters squared, and L per A is 7,750 millimeter per millimeter squared. Now this is the graph. As you can see, the larger the L per A is, the larger the resistance is. Now, summary of this experiment that throughout its room, several configurations of resistance pairs were tested for its setup. The slider on the slide bar bridge was adjusted until the multimeter reading reached 0. The corresponding lengths L1 and L2 were recorded, and the relationship was used to compute the unknown resistance. The results showed that the Wisdom bridge provides a sensitive and precise method for resistance measurement, especially for smaller resistance. As long as the bridge is properly balanced and the power supply voltage is kept in a safe range. Alright, that's everything that I can talk about today. Thank you for watching.